Select the major product of the following reaction. So looking at this reaction, I see that I am starting with a conjugated triene, that is 3 alkenes in this double bond, single bond, double bond alternating structure. I am adding to it HBr, and we know that HBr does electrophilic addition reactions to alkenes. And the other hint we have here is the temperature, 40 degrees Celsius. And so when you're looking at these reactions in your textbook, you'll see temperatures around 40 degrees and then temperatures in the range of -80. So this 40 degrees Celsius is our higher temperature for this reaction. And so this is the temperature that leads us to the thermodynamic or more stable product. And the more stable product is going to depend on the alkenes that we're left with. So we are looking for, it looks like we're going to have a diene left if we react just one equivalent and react one alkene. So we're looking for the more stable diene product. Okay, so now that we have an idea about that, we want to start this problem. And if you're looking for the most stable product, this means you really have to consider every possible product that can form. So I am going to draw the triene, and we're going to look at the mechanism for this reaction. So we're starting with HBr, and we need to know which alkene to react first. There's a process you could go through. We could protonate every single alkene and look at the carbocations that form. We could recognize we've got symmetry and look at the interior alkene and then the terminal alkenes. What I'm going to do is I'm going to jump to just the terminal alkene, recognizing that when I form that allylic cation, then I've got resonance stabilization with both alkenes. If I protonate in the middle, I break that extended conjugation, so I'm not going to do that. So either end, it doesn't matter. I'll start here, and we will get that first allylic carbocation. And what we're going to do is we're going to draw every possible carbocation and envision, okay, if the bromide attacks that carbocation, that is a potential product. So the first step is to draw all of these resonance structures. So there is the first one. And so if bromide were to add to that carbocation, and to keep it clean, I'm not going to draw the arrow, I'm just going to put the bromine there, then this would be one possible product. And this looks okay because we have alkenes that are conjugated. We know that conjugated alkenes are more stable than ones that are isolated. All right, so let's take a look at the next resonance structure. So we will move down the next bond. And if you want to make sure that you see every resonance structure, you want to go one bond at a time. Don't start doing more than one arrow. Okay, so we will have a pi bond here, a carbocation here, because we took the electrons away from that carbon, and then we still have that terminal alkene. If the bromide were to attack this structure, we would end up with the bromine here. That's an isolated diene. I'm going to say that's not the major product. All right, and so let's go one step further and move one more pi bond. And this will give us this diene and a positive charge out on the end. And so if the bromide were to add to this positive charge, we again have a conjugated diene. So this looks fairly stable. If we want to compare this conjugated diene to the first conjugated diene, so these are both conjugated. So that doesn't distinguish them. Then we're going to look at the substitution of the alkenes. So our first alkene, we have our first diene, we have one of the alkenes is di-substituted. The end alkene is mono-substituted. And if we look at our second conjugated alkene, we see that the first alkene is di-substituted and the second is also di-substituted. So this is your more stable product. which makes the answer C. These are the same, it's just flipped around.